Okay, so we're going to talk about hypothesis testing. There's a homework due Friday, which does some confidence interval tutorial. It requires a little bit of programming, modifying some of the code to do some bootstraps for t-distribution values. So check that out. Once you get the data loaded, so if you load the data set, the .r-data file in there, in your environment on RStudio, so you could see the environment up here. If there's any data that are loaded, like Bangladesh or the Minnesota groundwater, if those are up there, the command after the one that reads in the CSV file can operate. That is, sometimes you try to read in the CSV file, but it's not. But R doesn't know where it is. It doesn't know where it's stored on your computer. It'll give you a message saying that it can't find it, with kind of a cryptic remark in there that it can't access it somehow. But if the file's up there, or if you just type Bangladesh and it shows you all the data, then it's there and ready to go. And then the next commands could go. Right? And it has you deal with the alkalinity, or chlorine, right? No, alkalinity, right? But an example in the book runs through one for arsenic, I think, so a different one. So it's modifying the code, but changing the variable name in a couple spots to make it work out. So take a look at that. It's an example of doing that, right? So in hypothesis testing, is we get the overall perspective on hypothesis testing. Now we've done some things with hypothesis testing before. We did hypothesis tests with bootstraps and with permutations. And this one will primarily do hypothesis testing with so-called classical formulas for a few things. For one mean, for one proportion, for mu1 versus mu2, right? For comparing a couple, p1, p2, we're comparing a couple proportions. So we'll see a few different scenarios there and how the hypothesis testing go, right? But we'll also see something called likelihood ratio tests. And so the likelihood ratio test, like maximum likelihood estimation, makes use of the probability distribution function, joint distributions, for comparing hypotheses. And it's kind of a classic, a general framework for doing the testing that is quite useful. Right? So what did we do with hypothesis testing before? Well, this was back in chapter 3.3. Right? We had two groups. And we asked the question, are the means the same? So we start out with a null hypothesis that says, yes, they are the same. mu1 equals mu2. And an alternative could be just that they're different. In some contexts, you might clearly think one is larger than the other. Maybe there's some preliminary data or really solid rationale for that based on what you understand. Or you're concerned about, but generally we say they're different, right, as an alternative. And then we did a permutation test, where we randomly flipped some data from one group to the other, and our test statistic that we looked at was the x bar for one group minus the x bar for the other group, right? And we would observe a value. It wouldn't be 0. This one also implies that the difference is 0, versus this one implies that the difference, right, is not equal to 0. And so we look at that test statistic, and it's not going to be 0, but is it sufficiently far from 0 that we can justify a claim that there really is no difference, and that one group is bigger than the other. And so the permutation test, that under the null hypothesis, we simulate the sampling distribution of that. Right? So under the null hypothesis, or assuming that's true, we simulate the sampling distribution of the difference. Sampling distribution statistic. And so that's the nature of the permutations. Right? And so under the null hypothesis, this thing is centered at 0, and there's some sampling distribution there. Null hypothesis, right? There. And so we compared our actual statistic from our data as they really were gathered to the simulated distribution. And if it's too far out, then it's just not consistent with it, right? And so we calculate, look at the tail area, or the probability, what percent of our replications, our random permutations are greater than this. And if it's a small percentage, say less than 2.5%, if we're kind of doubling the probabilities because not equal is one way or the other, then we would reject. So if our statistic, if the actual, the real observed x bar 1 is too far out, so like the 2.5% tail, then we conclude that we reject the null hypothesis. Right? And conclude that there really is a difference. And that's how the logic went. Right? But what we want to do now is kind of repeat this process, but instead of using the simulated distribution, we want to use things that we know about sampling distribution from central limit theorem, very much like we did with the confidence intervals, like use t-distribution and other things to be able to calculate this probability, not by a simulation, but by the probability distributions. Right? But the overall logic, hypotheses are the same, test statistic is largely the same, or we'll standardize it to make a t-distribution. And then we're comparing it to a distribution, not necessarily simulated, but theoretical, and we get a little tail area. And again, if our probability of being out there under that reference distribution is small, we can't believe the null hypothesis anymore. Right? So we can chapter 8 really does this in, shows us a few different examples. So imagine we have a single sample, right? And we record x1, x2, right, to xn, and we calculate x bar and a standard deviation, and of course we have our sample size. So with one sample, our interest is going to be in the mean in this problem. Right, what is our question generally is what is the average in the population? One way to answer this is like we did in chapter 7, you make a confidence interval for it. That would tell you where it is, but sometimes you have a focused question. Is the population mean is equal to some specified value? This is sometimes called the null value. Or is it different? Where would mu sub 0 come from? Maybe that's the last year's value from a census. Right? Or maybe that's a scientifically agreed upon target value. Right? Maybe that's the value for one population you know about in depth. And now you've gone out and done a survey of another one. Is that surveyed population the same average as the one that you know as a reference? So we set up null hypotheses there. Is mu equal to mu sub 0 versus an alternative? Is mu not equal to mu sub 0? Again, you could have it larger or smaller depending on how you phrase the problem. And if the xi's, if the data are normally distributed, the xi's really are normal, right? Then taking the average, comparing the average to this null value, and dividing by the standard error, s over the square root of n, that thing, in repeated sampling, should have a t-distribution within -1 degrees of freedom. So we can compute this test statistic. That's our test statistic here. And if if that test statistic is far out, away from 0, because under the null hypothesis, if xi's are normally distributed, I guess I'd say and h0 is true, right? Because this has to be the mean to get it centered at 0. That would be a better statement to include that, right? And so if it is close to 0, you know, within kind of plus or minus 2 standard errors of the mean, then we can't reject use of 0. Right? But if it's more, all right, then it's pretty clear that other things being equal, that it's not use of 0. So if the RT statistic, or I'll say absolute value of it, is greater than, you know, the 0.975 level, right, the 97.5th percentile, if it's out there plus bigger than t, then we reject H0 at the alpha equals 0.05 significance level. The conclusion then is that use of 0 is not plausible. And you better think of it as being different, right? And so this 0.05 and this number here, where you get that cutoff, are very much related, right? And so this is saying 2.5% on the upper end, 2.5%. So you're setting a standard that says you have to be up that far, right? And you're dividing up the 5% into the two tails, and so that's at your level, right? And so you'd always communicate something about how you made that decision, what your cutoff, and by stating what type of significance level is there. Some people could say 1%, some people could say 10%, but if you say it's 5%, then people know how far out it should be. Right? The other way that this gets done is with a p-value. Right? So the p-value is going to be the probability we're at our value we observed or beyond, given that the null hypothesis is true. Right? Kind of a mouthful, right? But we can also compute this p-value. Right? It's the probability as extreme or more than the observed if H0 is true. So if we have our t statistic that we've computed, we can calculate say this is our t statistic value. And this is centered at 0, and this curve is a certain t distribution. This is this tail area, right? The probability that you're greater than that, looking up that way. And if the alternative is two-sided, we take this probability plus kind of an equal deviation on that other side, and so our p-value ends up being is 2 times the tail area. Right? And so if we have a certain significance level, like 0.05, we're going to reject the null hypothesis if our p-value is less than 0.05. We reject the H0 at the alpha, say 0.05 significance level. If our p-value is less than 0.05. Or if this was 1%, it could be the p-value less than 1%. But you have to get a small enough area out here. There's a 1-to-1 correspondence, right? If the p-value is small, that means the t-value is big. Right? And so sometimes it's phrased in terms of the t statistic or the p-value. Right? So let's look at one numerical example. The handout has, this is one problem from the book. For next Friday, there'll be some other problems to do from the book, but there's a nice collection of problems, so we'll look at one of these. So the mean cholesterol level of vegetarians in the United States is 161 milligrams per deciliter, and the distribution is normal. Right? You expect that the vegetarians from Sodor are different from vegetarians in the United States. You will conduct a study for a random sample of 24 vegetarians from Sodor. You you find a sample mean cholesterol of 164 with a standard deviation of 5 milligrams per deciliter. Do these data support the hypothesis that cholesterol levels for vegetarians in Sodor are different from the United States? All right, do you know where Sodor is? Ever heard of Thomas the Train?
Yeah.
Thomas the Train drives on the island of Sodor. I don't know if that's where this is, but you know. Right. Right, so we want to do this test. So what's our null hypothesis?
161.
So in the United States, we know it's 161, right? So we're going to say, is Sodor the same as what we know, right? Yeah. So in this one, the null hypothesis is that the mean is 161 milligrams per deciliter, same as US. So the alternative could be just that it's not that. If you knew that some area was impoverished or had a certain diet that was shown to be problematic in the past, you might make it one way, but it's fine to just make it two-sided. We observe for how many people? 24. That X bar is 164, and the standard deviation in the sample is 5, again milligrams per deciliter. Right. So we had to form our null hypothesis we stated. So our t statistic is we take the X bar minus mu sub 0, mu sub 0, right, is 161, right, over S over the square root of n. So 164 minus 161, and then 5 over square root of 24, which is almost like 5. So this is almost like 1 down here. So this is going to be pretty big, probably. It ends up being 2.94. So that's a pretty big t-value, right? As our t-statistic. The degrees of freedom we'll use in the t-distribution for comparison is 23. The 97.5 percentile for this particular t-distribution is 2.07. Right? So what do we conclude? Do we stay with the null hypothesis, or do you reject it? We reject, right? The t-statistic is bigger than this reference distribution. So we do have a picture where here's this, here would be the 2.07, but our actual value of 2.94 is somewhere right out here. So if we've done a simulation in some way, right, and made a histogram of the values of this t-statistics, we'd be out here. Or if you just did the difference of x bars versus mu, if you could simulate under the null hypothesis being true, you would be out there. So okay. Skip the page, huh? Back. So we would reject the null hypothesis. Right? So conclusion. So because, maybe you shouldn't start sentences with because, but whatever. Because our t-statistic is greater than 2.07, we're going to reject the null hypothesis at the alpha 0.05 significance level. Right? And conclude that the cholesterol in Sodor is lower than the U.S. average. No, is greater than the U.S. average. That's only 3 points, 3 milligrams per deciliter. So, is that a big impact on health? You know, I'm not sure, but maybe scientifically, maybe it is. Right? Maybe it's not that big a thing, but given that the standard deviation was so small, it comes out as significant. Right? So doing that on the computer, so you get summaries like that, you can just type things in. So this handout, the second handout, right, does some things with this. Right? So previously we did a confidence interval, right, for the mean. Right? Our confidence intervals had the mean plus or minus a t-value times standard error. Right? So if we made a 95% confidence interval for the cholesterol and Sodor, it go from about 162 up to about 166. Right? So our confidence interval doesn't include 161. Right? So it does not seem like a reasonable value here. I think in this next part, for some reason, reversed things. The statistics should have been 164 minus 161. So it should be a positive value out there. I don't know yet, so I just a mental error there. So x bar minus mu sub 0 divided by the standard error, and you get the 2.94 value. And the lower t-value and the upper t-value that would cut off by 2.5% each is 2.07, or the negative, right? And we're more extreme than that, so we reject. Right? What's the probability we're actually bigger than that 2.94 value? Right? And again, I think I kind of reversed the direction there. Right? Right, so if we calculate the p-value, right, we want the probability that a t-distribution with 21 degrees of freedom is greater than 2.94. Right? And that's pretty small. It's a 0.0037. And so the p-value is twice that. We count evidence above or below the actual mu sub 0 equally, and so we'd be equally concerned. 74. And that's pretty small. Right? So less than 1% chance if the null hypothesis is really true. Right? And so because the p-value is less than 0.05, we can reject the null hypothesis. And include cholesterol. It's higher on average. And so it's right? On average 5 points or 3 points higher, right? Based on this sample. Right, so it's good to take however you phrase it in terms of the t-statistic or the p-value, and then take it back and phrase it in terms of what you actually see in terms of the average. Which group is it higher or is it lower? And say that it's significantly different, and what significance level you're thinking about. Yeah.
Are there like different contexts in which you'd report a t-value versus a p-value? A t-statistic versus a p-value? What's the purpose of having both?
You just kind of have to go along with the whole process it's just a computation that you would do for both.
Oh.
The p-value, right, takes into account the t-distribution, and so I think it's a little easier to state in an article, okay, the p-value is this, then you don't need to take, say, the t-distribution and the degrees of freedom and then think about looking it up. Right? I think saying the p-value itself, like 0.007 or less than 0.01, gives a little more information than just saying it's less than 0.05, right? Because the smaller this is, generally the stronger the evidence is and more convincing it is, right? If this had come out to be 0.04, well, it's a little bit less than that. It's still significant. It still qualifies. But if you say it's smaller, less than 0.01, then it's a little more detailed. So I think generally giving more details better, giving the X bar you have, the standard deviation, the sample size, which test did you do, p-value, Once you have the p-value and know some of that other information, you could figure out the t-statistic if you wanted. Yeah.
Is p-value always 2 times the tail, or is it?
No, so if we had done a one-sided hypothesis, right? So if you started out, it's tied to that alternative. So if the alternative was that the mean is 161, but the alternative was that it's less than 161, and, or greater, it's greater than, right, so, greater. And then x bar is 164, right? Our t-statistic is still going to be the same thing, 164 minus 161 s over the square root of n. We're still going to get 2.94. And we're going to calculate the probability that a key distribution with 23 degrees of freedom, because n was 24, is greater than that. And if we're only looking in one direction, if it's one-sided, right, then we don't need to double it. Because we're only considering evidence on that one side. When is it appropriate to do that? Well, you know, if obviously you can get a smaller p-value by looking at one side, right? So if you look at your data and say, oh, it must be bigger, and so therefore I'm going to use a one-sided. That's kind of, we would say cheating, or it's, you know, kind of looking at your data and then forming a hypothesis is not quite the same as stating something up front and then trying to prove it. Usually, you know, in clinical trials in medicine, the hypothesis has to be stated before any data is collected. Like you have to write down a one-sided hypothesis if that's what you're going to do, and justify why that's reasonable, right? And then you go out and collect the data and report on what you found. And they usually, you know, report the ones, you know, what type of, is it a one-sided or two-sided? And there's places that record things for clinical trials. Clinicaltrials.gov, you can register your clinical trial before it ever starts. And then when they say, well, did you search through your data to find hypotheses? No, it was written down as a protocol. This was the main hypothesis and everything. And so it's a higher standard of proof. Because if you're checking 100 different blood chemicals and chose the ones that had the biggest significant results, and did it all one-sided, say, oh, look, all these things I found, people will say, you know, there's no way that we believe you. Because you search through your data, of course you're going to find something by chance, right? And it's not very convincing. So usually register it, state clearly, is it a one-sided or two-sided hypothesis test? And the major medical journals won't publish it unless it was registered beforehand. So. Now, there are some criticisms of using p-values and debate over their usefulness, because in some fields it's been pretty loose, and where there'll be a study done, in some fields there is a tradition of registering things beforehand and stating hypotheses and having a whole prospectus of what you think is going to happen. And therefore, it's kind of prone to kind of abuse or searching for significance, or checking through the data to find maybe this is true not for Sodor, but maybe half of Sodor, right? And so it's kind of interesting exploration, I think worth doing, but it doesn't have quite the same, you know, meaning in terms of proving something. And some of these p-values are reported, you know, in some polls that have 20 or 30% response rates, or even less, like internet polls that have 1 or 2% response rates. People will do testing and report p-values. Like, well, does that p-value mean that it's really that significant? Like, what if you got those people who refused to actually participate? Would the results be the same? It's kind of potentially for a lot of bias. So these things always have to be kind of taken in context, right? If it's a really serious study that's pre-registered and they seem to adhere to the greatest protocols, hopefully that study could then be replicated by new researchers, right? Or carry over and have some meaning for a new context. So it's challenging. There's some debate about what this means in the modern context with thousands of studies going on and kind of loose data collection in some places. But it's still, you know, the way it would be done. Is there anything else on the computer part of this? No. You can look up the cutoff values there for different things. Right? Another way that we started talking about two samples. So x1, x2, right, up to xn, and y1 and y2 up to ym. Two samples that are independent of each other. We can ask a question, do the two samples from different populations or different groups have the same average? So we can ask a null hypothesis, are these the same versus the way, are they different? Right. Right. So our test statistic in this case is going to be based on the sample differences under the null hypothesis. We're going to, this implies that mu1 minus mu2 equals 0. So trying to 0 doesn't change the value, of course. In some cases, you might think that there's a difference, right? So if you think that are things increasing with inflation, then there'd be a certain percentage increase or something like that. But you might not have a non-zero value. If it's non-zero, you put the difference there. And then we need the standard error for this. Right? Like we did with confidence intervals, we'll take the sample variance of the x's, it's called x, and then the sample variance of the y's for the second group over its sample size, and take that, right? And we'll compare that to a t-distribution with some degrees of freedom. Right? And this is where, right, we have that Welch degrees of freedom thing for a confidence interval, that it's not exactly a t, right? So, and then we'll calculate a p-value. And if the null hypothesis, calculate the p-value kind of the same way, and if the p-value is small and this t-statistic is extreme, we'll reject the null hypothesis. If we can pool the variances, if the two variances are the same, then we'll kind of pool the two standard deviations and get a combined estimate of that, and then have the two sample sizes. And that will be our standard error. And in this thing, we'll have a t-distribution of n plus m. It does have a specific t-distribution. This one was this kind of approximation by Welch to do that. So let's look at kind of going through this a little faster. It's kind of the same logic. Some of the formulas come from what we had for confidence intervals. Let's look at a numerical example. So in the problem 8.7, this one, right? So researchers at the Minnesota Pollution Control Agency collected samples of fish in different lakes. And these were mercury levels in parts per million for the fish in 2 lakes. Right? It looks like they've already sorted the data, right, within each group. They have 9 observations in each, but there's no indication that these are matched in any way. Right? Do the data suggest that the true mean mercury levels differ for the 2 lakes? Set up and carry out a significance test and state your conclusion.
So significance test is a hypothesis test?
Yeah, so significance test, hypothesis test of the statistical significance of that. So in R, you can enter the data. And so setting up this vector here, Whitewater and Worth is the other area. The average of so now Whitewater is just a string of numbers. Right? And Worth is just a string of numbers, and they show up here as data things that you have. And so the average is 2.96 or 2.57, so the difference is 0.39, right? There's standard deviations for both groups. Those are not quite equal. They're not too different. I might tend to pool them. I think it would be reasonable to do that. Both of them have length 9, so the sample sizes are 9. The difference in the averages is 3.039. This is the variance formula. So standard deviation squared is variance. The variance of those things. So we get a standard error. Oops. Okay. Get all that. Right. So with the difference of 0.039 and a standard error of 0.015, is this a significant result? the absolute difference from 0 is 0.039. 1 standard error is 0.01. So this is more than 2 standard errors away.
So it's significant.
Yeah, it's 2 point something standard errors away. Now, I didn't do the large formula for the Welch degrees of freedom. Right? The conservative things to do is use the smallest that you would use if you had only one sample. So if I used 8 and wanted to make a confidence interval, I take the average difference, plus or minus a t-value with only 8 degrees of freedom times that standard error, and I get 0.0044 up to 0.07 something as a 95% confidence interval for the average difference, right? So am I going to believe 0? Am I going to believe these things are equal? Right? The interval misses 0. Right? It's above that. So 0 is not included in what's reasonable. T-test, t.test command, you put the one column there, the other one there, and run it. And it comes out looking like this. The t-statistic is about 2.6. Right? The degrees of freedom it says to use is about 13.9. Right? There was 9 in one group, 9 in the other, so that's 18 minus 2 would be 16. We're going to be somewhere between 8 and 16, so what it says. And it gives a p-value there, 0.02. It also gives a 95% confidence interval, which is pretty close to ours, but we use a different t-value. And so some useful things there. Right? And because the p-value is small, we reject the null hypothesis. And these two lakes do not seem to be equal. The first lake, Whitewater, first lake is Whitewater, right, is the higher average. So you could say it's significantly higher average at the 5% significance level. Right? If you wanted to do this, right? So yeah, if I made my confidence interval better, if I changed the degrees of freedom here to match that one for Welch, we get the results that they had. The other way here's it just doing the t-statistic, right, the Whitewater, the difference in means, and here's this right standard error formula in there. You can type it all there. You get 2.599. That's the t-statistic. Here's the p-value, 0.021. There is, I take 1 minus the probability, the pt thing by default goes below a value. Right? So if I want above the value, I have to take 1 minus that, or tell it to take the upper tail. You just got to make sure that if you really expect to get a small value like 0.05 or something, that you're looking in the right direction. So anyway, there's that. If you think these are, now let's look at the data a little bit. What does the Whitewater look like? Right. Not really too normal looking, and Worth a little more symmetric. I mean, this is 9 observations, not too many. So, one concern would be that the central limit theorem doesn't really work so well here, right? And that our p-values, assuming the data are normal or we have somewhat large sample sizes, might not be too accurate. Right? With only 9 observations in each, I'd be kind of interested to see what a permutation test would say. Right? If we simulate like that, does it does it come up with a similar p-value? These p-values, 0.02 is reasonably small. Maybe it would change a little bit. I wouldn't think it would change a whole lot. But anyway, it might be, that's small of a sample size. If you really wanted to kind of be convincing, you might do the permutation test as well to see what you get. The other way to do this t-test, right, that I didn't put on here, if the variances are equal, if you think the variances are equal, you can tell it to do it var.equal equals true, and it does this 2-sample t-test. Degrees of freedom are now 16 because we're using one estimate of the pooled variance. Confidence intervals are similar. The t-statistic actually looks like exactly the same value. Right? The p-value is pretty much identical. Right? So even though one variance was 0.2, standard deviation was 0.25, the other 0.38. They're not drastically different. So it doesn't change the result, which is a good thing. Right? But any questions about the logic of doing it? Right, set up the hypotheses. The next two cases, we could talk about them briefly. The next case is we have one sample and we're questioning whether the proportion equals some value. Right? And the alternative is that it's not equal to that, or I think in one of the data examples, it's asking is a rate higher? So is the proportion equal to some number of p sub 0? No, actually higher than p sub 0. And so we can form, there's different ways to do this one, but we can compare, we'll probably come back to this in some detail about it, about continuity correction and a little more nuance of this one. Right. But under the null hypothesis, P hat is going to be approximately normally distributed around its P0 as long as n is not too small. Right? And what's its variance? Well, in general, we had P1 minus P over n as the variance from a binomial formula. But now the null hypothesis says that it's actually P sub 0. And so when we divide by a standard error, or we're here to standardize this thing, we're going to put in our null value here. So if the null hypothesis is true, we've standardized this normal. And so if the null hypothesis is true, and really we haven't changed from that p sub 0, our z statistic is distributed as a standard normal. And so we'll reject the null hypothesis. We could say reject null hypothesis at the alpha 0.05 level, significance level, if our z statistic, well, this is one-sided, isn't it? I made it one-sided. So we think that we actually are going to be greater than that. If z is greater than, because it's one-sided, we don't use 1.96 as a cut. We have to use a place that cuts off 5%, right, which is at 1.645. So a little bit different cutoff because it's one-sided. Or if you calculate the probability under the normal, then you would do one-sided. So we'll come back to a few details of this. It's going a little fast, I think, but let's look at one example anyway. Right? So 8.14, right? For this one. In 1987, 39.1% of sex workers in Mali were HIV positive. A sociologist suspects this proportion is higher today. So where would they know this from 1987? Why would they believe it's that rate? Maybe that's determined by a survey. Maybe they had a much larger survey or something like that. Maybe they got that from some type of medical records or hospital records or something. So that came from somewhere. Right? But to check comparing it today, he surveys 130 sex workers from Bamako and finds p hat equals 0.48, so 48%. is this sufficient evidence to conclude that the proportion of sex workers in Bama cohort HIV is greater than that? Right? That's the motivation for a one-sided hypothesis. So, doing that, how many actually said yes, they're positive? Now, 48% was the percentage. Right? But what is 48% of 130? Well, it's either 62 or 63, right? It's not clear exactly which one that is. Right? 130 times point was 62.4. 62 over 130 would round to 48. Right? But 63 over 130 would also round to 48. So I'm not totally sure which it is. Right? The proportion test command in R can test it in any case. Right? So if we think it's 62, right? And out of 130, this is X and this is N. This is our null hypothesis. Right? Value goes in there. And we can give an alternative that it's greater than that. Right? So it's going to be a one sample proportion test. There's a little bit of extra information in here. But it gives us a p-value of 0.02757. It also gives a one-sided confidence interval, right? That is bigger than the 0.391. So because this p-value is small, we're going to reject the null hypothesis and conclude that it has gotten worse. It has increased. Now, if it's 63, is the p-value going to go up or down? Down. Why is it going to go down? Let's see, what with 130 times 0.391? That would imply about 51. Right? Should say yes. And we checked out before 62 saying yes and got a p-value. Now we're looking at 63 saying
so
yes.
it should be
So the p-value will go down. Right? The z-value should go up. Right? So think about those things. Right? So you're moving farther away from the null hypothesis, so you should get a smaller p-value.
Right? More strongly rejected.
You more strongly reject it. You move out further, the tail area becomes smaller, p-values can be smaller. It's a good thought exercise to think about how those things change. Statistics is the z-value is going to get bigger, but that means that the tail area is smaller. Right? So you reject, you're more sure of it. So 62, 63, when you do that, the p-value is now 0.01797. So it's dropped from 0.028 to 0.018. So it's smaller. So you still reject at the 5% significance level, and we get kind of the same conclusion. Now if you just do so the p hat, how would you do the z-value? So p hat minus the 0.391, right? And then the square root of 0.391 times 0.6609 is 1 minus that. And it said there are 130. Right, so that's going to get a z-value of about 2.08, right? Following that formula. A z-value of 2.08. What's the probability we're bigger than that from a normal? Right? There's a probability for z. If you put 2.07957 in there, p norm, right? It's not pz, it's p norm, right? You get about 98% is less than that, right? So what's the chance you're bigger than that? Because that's away from the null. Is 1 minus that, or lower tail equals false. Right? Give that upper. Right? If you're not doubling it, it's not a two-sided test, then that's the p-value. But we'll come back to that one. We look at it a little more carefully, kind of running through it quickly to see kind of the similarity of the logic of these things. Right? So you do data, calculate some statistic, and then under a reference distribution, you see is it extreme. The last example, just to
And we're using normal because it was proportion instead
because
of
it's proportion.
for mean.
Yep. The why t versus z? It's a little, seems a little confusing, right? Why not t all the time or something, right? But there's different probability limits for normals. Well, if you have normal data, there's the t statistic is exactly a t distribution, and so we use t there. For the binomial, there's not quite the same properties. A limit of a binomial, a standardized binomial, becomes a normal. So we use normal for that. There's not quite the same probability theory. And at the end of the probability books, they do the distributions derived from the normal and the limit, central limit theorem, and they're just two different results, so they use the two different. Still, we want them to perform well in large, over time. We want 95% confidence intervals to cover 95%. And if the null hypothesis is true, we don't want to reject too much, 5%. And so it seems to work with the different data types. Right? The last problem, just to kind of give another context example, we can go back through some formulas. Right? Are there regional differences in support for same-sex marriage? Right? So the Pew Research Center for the People in the Press is based in Washington, D.C. They still do a lot of large-scale surveys and polls. They're heavily involved in things like American Association for Public Opinion Research, or APOR, and survey research section of American Statistical Association. So they have some pretty serious people in terms of theory and estimation and things. Right? So they found that 62% of 552 people from the Midwest supported same-sex marriage, and then 68% of 557 from the West supported same-sex marriage. So 62 versus 68, there's a percentage difference there. Is that statistically significant? Is that more than just chance variability, right? Because you survey any two groups, you're going to get a different number. But is it, is it significantly different? Is 6% meaningfully different? Is that going to affect communities and how people behave and how they fund, laws that they pass? That 6% difference, could be meaningful. So if we wanted to test that, this proportion test can be done. 62% of 522 is about 342 people. This one out of 577 is about 392 people. And so you can put the, prop.test, you put the 340, assume that one's 342, assume this one's 392. And then we have 552 as one sample size and 577 as the other sample size. It will do a test to see whether these things are significantly different. There's something here called chi-squared or x-squared. Eventually we'll see what that statistic is. That's another way of phrasing it. But the p-value comes out to 0.04. So it's statistically significant. It's more than chance. Not a whole lot more, and it's 6%. So, but it would be marked as statistically significantly different. It's a two-sided test. This x squared, if you kind of take the square root of, that, it's kind of like a z-value, right? Roughly. Right? And so a z-value about 2.04 would be significant at the 5% level. Right? So this chi-squared or x-squared statistic shows up there, but it kind of has a same type of meaning there in this context. So that's returning to hypothesis testing, right? So we can use some of the formulas we've done to look at a bunch of different problems. We'll come back on Friday and look at a few more details of work we're doing, a little more terminology.
You turn it into a whole matrix, so
So you
it's,
move this into
yeah, basically you just turn it into a matrix with 4 columns and 3 rows.
there, and set that as the,
That would be the 4th column.
okay.
And then you just put it into reduced row echelon, so each one of these is like echelon.
Okay, each one's the columns, got it, okay.
Yeah. At least that's how it seemed for me when I went for help.
Okay.